Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Data Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You work for a shipping company that has distribution centers where packages move on delivery lines to route them properly. The company wants to add cameras to the delivery lines to detect and track any visual damage to the packages in transit. You need to create a way to automate the detection of damaged packages and flag them for human review in real time while the packages are in transit. Which solution should you choose? The options are: Option A, use BigQuery machine learning to be able to train the model at scale, so you can analyze the packages in batches. Option B, train an AutoML model on your corpus of images, and build an API around that model to integrate with the package tracking applications. Option C, use the Cloud Vision API to detect for damage, and raise an alert through Cloud Functions. Integrate the package tracking applications with this function. Option D, use TensorFlow to create a model that is trained on your corpus of images. Create a Python notebook in Cloud Data Lab that uses this model so you can analyze for damaged packages.
To arrive at the correct answer, we focus on the keywords: detect and track any visual damage, automate the detection, real-time.
The correct answer is option B. Train an AutoML model on your corpus of images, and build an API around that model to integrate with the package tracking applications.
Why is this correct? B. AutoML Vision allows you to train a custom machine learning model on your own images to detect specific damage. Building an API around it meets the real-time integration requirement. Why are the others incorrect? A. BigQuery ML is intended for structured tabular data, not images. Additionally, batch processing contradicts the requirement for real-time detection. C. The standard Cloud Vision API is pre-trained on generic objects and cannot reliably identify custom visual damage specific to the company's packages. D. A Python notebook in Cloud Data Lab is used for interactive data exploration and model development, not for automated, real-time inference and production.
You are migrating your data warehouse to BigQuery. You have migrated all of your data into tables in a dataset. Multiple users from your organization will be using the data. They should only see certain tables based on their team membership. How should you set user permissions? The options are: Option A, assign the users/groups data viewer access at the table level for each table. Option B, create SQL views for each team in the same dataset in which the data resides, and assign the users/groups data viewer access to the SQL views. Option C, create authorized views for each team in the same dataset in which the data resides, and assign the users/groups data viewer access to the authorized views. Option D, create authorized views for each team in datasets created for each team. Assign the authorized views data viewer access to the dataset in which the data resides. Assign the users/groups data viewer access to the datasets in which the authorized views reside.
To arrive at the correct answer, we focus on the keywords: migrated all of your data into tables in a dataset, only see certain tables based on their team membership, set user permissions.
The correct answer is option A. Assign the users/groups data viewer access at the table level for each table.
Why is this correct? A. BigQuery supports table-level IAM policies. Assigning data viewer roles directly at the table level is the most straightforward and native way to restrict users so they only see specific tables based on their team membership, avoiding unnecessary complexity. Why are the others incorrect? B. Standard SQL views do not grant access to underlying data. Users would still need permissions on the underlying tables to query the views, which defeats the purpose of restricting access to specific tables. C. Authorized views grant access to query results without exposing underlying tables, typically for row or column level security. They are overly complex and unnecessary when you simply need to restrict access to entire tables. D. Creating separate datasets with authorized views was a legacy workaround before BigQuery introduced table-level IAM permissions. It is an anti-pattern for simple table-level access control due to excessive administrative and architectural overhead.
You want to build a managed Hadoop system as your data lake. The data transformation process is composed of a series of Hadoop jobs executed in sequence. To accomplish the design of separating storage from compute, you decided to use the cloud storage connector to store all input data, output data, and intermediary data. However, you noticed that one Hadoop job runs very slowly with Cloud Dataproc, when compared with the on-premises bare metal Hadoop environment, 8 core nodes with 100 GB RAM. Analysis shows that this particular Hadoop job is disk I/O intensive. You want to resolve the issue. What should you do? The options are: Option A, allocate sufficient memory to the Hadoop cluster so that the intermediary data of that particular Hadoop job can be held in memory. Option B, allocate sufficient persistent disk space to the Hadoop cluster and store the intermediate data of that particular Hadoop job on native HDFS. Option C, allocate more CPU cores of the virtual machine instances of the Hadoop cluster so that the networking bandwidth for each instance can scale up. Option D, allocate additional network interface card (NIC) and configure link aggregation in the operating system to use the combined throughput when working with cloud storage.
To arrive at the correct answer, we focus on the keywords: separating storage from compute, store all input data, output data, and intermediary data. Hadoop job runs very slowly, disk I/O intensive.
The correct answer is option B, allocate sufficient persistent disk space to the Hadoop cluster and store the intermediate data of that particular Hadoop job on native HDFS.
Why is this correct? B. Native HDFS on persistent disk provides much faster disk I/O performance compared to Google Cloud Storage. Storing intermediate data on native HDFS directly resolves the disk I/O bottleneck for this intensive job. Why are the others incorrect? A. The bottleneck is disk I/O intensive, not memory capacity. Simply allocating more memory won't automatically resolve disk I/O issues for this job without impractical application rewrites. C. While adding CPU cores increases network egress bandwidth to cloud storage, the job is explicitly described as disk I/O intensive. Native HDFS on persistent disks is a more direct and effective solution. D. Network bandwidth to cloud storage is governed by the number of vCPUs per VM instance, not by the number of NICs. Adding NICs will not increase overall bandwidth or resolve the I/O bottleneck.
You work for an advertising company, and you've developed a Spark ML model to predict click-through rates at advertisement blocks. You've been developing everything at your on-premises data center, and now your company is migrating to Google Cloud. Your data center will be closing soon, so a rapid lift and shift migration is necessary. However, the data you've been using will be migrated to BigQuery. You periodically retrain your Spark ML models, so you need to migrate existing training pipelines to Google Cloud. What should you do? The options are: Option A, use Vertex AI for training existing Spark ML models. Option B, rewrite your models on TensorFlow and start using Vertex AI. Option C, use Dataproc for training existing Spark ML models, but start reading data directly from BigQuery. Option D, spin up a Spark cluster on Compute Engine and train Spark ML models on the data exported from BigQuery.
To arrive at the correct answer, we focus on the keywords: Spark ML model, rapid lift and shift migration, BigQuery, migrate existing training pipelines.
The correct answer is option C, use Dataproc for training existing Spark ML models, but start reading data directly from BigQuery.
Why is this correct? C. Dataproc is Google Cloud's managed Spark service, ideal for a rapid lift and shift migration of existing Spark pipelines. The Spark BigQuery connector allows Dataproc to efficiently read data directly from BigQuery without intermediate exports. Why are the others incorrect? A. Vertex AI is designed for custom training in standard ML frameworks, but it does not provide a managed Hadoop/Spark environment needed for lifting and shifting existing Spark ML pipelines. B. Rewriting the existing models in TensorFlow would require significant development time and effort, which directly violates the requirement for a rapid lift and shift migration. D. Manually deploying Spark on Compute Engine introduces unnecessary operational overhead compared to Dataproc. Furthermore, exporting data from BigQuery is inefficient because the Spark BigQuery connector supports direct reads.
You work for a global shipping company. You want to train a model on 40 terabytes of data to predict which ships in each geographic region are likely to cause delivery delays on any given day. The model will be based on multiple attributes collected from multiple sources. Telemetry data, including location in GeoJSON format, will be pulled from each ship and loaded every hour. You want to have a dashboard that shows how many and which ships are likely to cause delays within a region. You want to use a storage solution that has native functionality for prediction and geospatial processing. Which storage solution should you use? The options are Option A, BigQuery. Option B, Cloud Bigtable. Option C, Cloud Data Store. Option D, Cloud SQL for PostgreSQL.
To arrive at the correct answer, we focus on the keywords 40 terabytes of data, GeoJSON format, native functionality for prediction and geospatial processing.
The correct answer is option A, BigQuery.
Why is this correct? A. BigQuery is a serverless data warehouse that seamlessly scales to petabytes. It natively supports both geospatial processing through BigQuery GIS and machine learning prediction through BigQuery ML, making it ideal for this 40 terabytes dataset. Why are the others incorrect? B. Cloud Bigtable is a NoSQL database optimized for high-throughput reads and writes. It does not provide built-in native functionality for machine learning prediction or complex geospatial processing. C. Cloud Data Store is a NoSQL document database for transactional apps. It is not designed for 40 terabytes analytical queries and lacks native machine learning and comprehensive geospatial features. D. Cloud SQL for PostgreSQL supports geospatial data via PostGIS, but its scaling limits make it unsuitable for 40 terabytes analytical workloads. It also lacks native built-in machine learning capabilities like BigQuery ML.
You operate an IoT pipeline built around Apache Kafka that normally receives around 5,000 messages per second. You want to use Google Cloud Platform to create an alert as soon as the moving average over 1 hour drops below 4,000 messages per second. What should you do? The options are Option A, consume the stream of data in Dataflow using Kafka I/O. Set a sliding time window of 1 hour every 5 minutes. Compute the average when the window closes, and send an alert if the average is less than 4,000 messages. Option B, consume the stream of data in Dataflow using Kafka I/O. Set a fixed time window of 1 hour. Compute the average when the window closes, and send an alert if the average is less than 4,000 messages. Option C, use Kafka Connect to link your Kafka message queue to pub/sub. Use a Dataflow template to write your messages from pub/sub to Bigtable. Use Cloud Scheduler to run a script every hour that counts the number of rows created in Bigtable in the last hour. If that number falls below 4,000, send an alert. Option D, use Kafka Connect to link your Kafka message queue to pub/sub. Use a Dataflow template to write your messages from pub/sub to BigQuery. Use Cloud Scheduler to run a script every 5 minutes that counts the number of rows created in BigQuery in the last hour. If that number falls below 4,000, send an alert.
To arrive at the correct answer, we focus on the keywords Apache Kafka, alert as soon as moving average over 1 hour drops below 4,000 messages per second.
Correct answer is option A. Consume the stream of data in Dataflow using Kafka I/O. Set a sliding time window of 1 hour every 5 minutes. Compute the average when the window closes, and send an alert if the average is less than 4,000 messages.
Why is this correct? A. Dataflow provides native Kafka I/O. A sliding time window computes a continuous moving average, satisfying the requirement to alert as soon as the average over the past hour drops. Why are the others incorrect? B. A fixed time window computes the average once per hour, rather than continuously tracking a moving average. C. Kafka Connect, Pub/Sub, Bigtable, and Cloud Scheduler create an overly complex pipeline that does not natively support continuous stream processing. D. Using BigQuery for streaming analytics and querying it every 5 minutes is inefficient and an anti-pattern compared to native stream processing.
You plan to deploy Cloud SQL using MySQL. You need to ensure high availability in the event of a zone failure. What should you do? The options are: Option A, create a Cloud SQL instance in one zone, and create a failover replica in another zone within the same region. Option B, create a Cloud SQL instance in one zone, and create a read replica in another zone within the same region. Option C, create a Cloud SQL instance in one zone, and configure an external read replica in a zone in a different region. Option D, create a Cloud SQL instance in a region, and configure automatic backup to a cloud storage bucket in the same region.
To arrive at the correct answer, we focus on the keywords: Cloud SQL, MySQL, high availability, zone failure.
The correct answer is option A. Create a Cloud SQL instance in one zone, and create a failover replica in another zone within the same region.
Why is this correct? A. Creating a failover replica in another zone within the same region provides high availability for Cloud SQL. If the primary zone fails, the failover replica automatically becomes the primary instance. Why are the others incorrect? B. Read replicas are designed for read scalability, not high availability. They do not automatically fail over if the primary instance goes down. C. External read replicas are used for replicating data outside of Cloud SQL. They do not provide automatic failover for high availability. D. Automatic backups provide data durability and point-in-time recovery, but they do not ensure continuous high availability in the event of a zone failure.
Your company is selecting a system to centralize data ingestion and delivery. You are considering messaging and data integration systems to address the requirements. The key requirements are the ability to seek to a particular offset in a topic, possibly back to the start of all data ever captured, support for publish/subscribe semantics on hundreds of topics, retain per key ordering. Which system should you choose? The options are: Option A, Apache Kafka. Option B, Cloud Storage. Option C, Dataflow. Option D, Firebase Cloud Messaging.
To arrive at the correct answer, we focus on the keywords: seek to a particular offset in a topic, publish/subscribe semantics, retain per key ordering.
Correct answer is option A, Apache Kafka.
Why is this correct? A. Apache Kafka explicitly supports topic offsets, allowing replay of captured data. It provides publish/subscribe semantics and guarantees per key ordering within partitions, perfectly matching the required ingestion and messaging capabilities. Why are the others incorrect? B. Cloud storage is an object storage service, not a messaging system. It does not natively provide topic offsets, pub/sub semantics, or per key ordering. C. Dataflow is a stream and batch processing engine, not a data ingestion or messaging system. It processes data but doesn't manage topics or offsets directly. D. Firebase Cloud Messaging is designed for sending notifications to client applications, not for serving as a centralized, high-throughput enterprise data integration system with offset seeking.
You are planning to migrate your current on-premises Apache Hadoop deployment to the cloud. You need to ensure that the deployment is as fault-tolerant and cost-effective as possible for long-running batch jobs. You want to use a managed service. What should you do? The options are: Option A, deploy a Dataproc cluster. Use a standard persistent disk and 50% preemptible workers. Store data in cloud storage, and change references and scripts from HDFS // to GS // Option B, deploy a Dataproc cluster. Use an SSD persistent disk and 50% preemptible workers. Store data in cloud storage, and change references and scripts from HDFS // to GS // Option C, install Hadoop and Spark on a 10-node compute engine instance group with standard instances. Install the cloud storage connector and store the data in cloud storage. Change references and scripts from HDFS // to GS // Option D, install Hadoop and Spark on a 10-node compute engine instance group with preemptible instances. Store data in HDFS. Change references and scripts from HDFS // to GS //
To arrive at the correct answer, we focus on the keywords: Apache Hadoop deployment, fault-tolerant, cost-effective, long-running batch jobs, managed service.
The correct answer is option A, deploy a Dataproc cluster. Use a standard persistent disk and 50% preemptible workers. Store data in cloud storage, and change references and scripts from HDFS // to GS //
Why is this correct? A. Dataproc is a managed Hadoop service. Using preemptible workers reduces costs. Storing data in cloud storage, GS // ensures fault tolerance by decoupling storage from compute. Standard persistent disks are more cost-effective than SSDs for long-running batch jobs. Why are the others incorrect? B. While Dataproc is correct, using SSD persistent disks increases costs unnecessarily. Standard persistent disks are sufficient and more cost-effective for long-running batch workloads. C. Installing Hadoop on compute engine creates a self-managed cluster, which violates the requirement to use a managed service. It also lacks preemptible instances for cost savings. Why are the others incorrect? D. This is an unmanaged solution. Furthermore, storing data in HDFS on preemptible instances is highly risky and not fault-tolerant, as preemptible instances can be terminated at any time, risking data loss.
Your team is working on a binary classification problem. You have trained a support vector machine (SVM) classifier with default parameters, and received an area under the curve (AUC) of 0.87 on the validation set. You want to increase the AUC of the model. What should you do? The options are: Option A, perform hyperparameter tuning. Option B, train a classifier with deep neural networks, because neural networks would always be SVMs. Option C, deploy the model and measure the real-world AUC, it's always higher because of generalization. Option D, scale predictions you get out of the model, tune a scaling factor as a hyperparameter, in order to get the highest AUC.
To arrive at the correct answer, we focus on the keywords: support vector machine, SVM, classifier with default parameters, increase the AUC.
The correct answer is option A, perform hyperparameter tuning.
Why is this correct? A. The model was trained with default parameters, so performing hyperparameter tuning is the appropriate next step to optimize performance and increase the AUC. Why are the others incorrect? B. Deep neural networks do not always outperform SVMs. Model performance depends on the specific dataset, problem complexity, and available data volume. C. Real-world AUC is not inherently higher. In practice, performance on real-world data is often lower than on the validation set due to distribution shifts and unseen variations. D. AUC evaluates the ranking of predictions, not their absolute values. Applying a uniform scaling factor does not change the relative ordering, so the AUC will remain exactly the same.
You need to deploy additional dependencies to all nodes of a Cloud Dataproc cluster at startup using an existing initialization action. Company security policies require that Cloud Dataproc nodes do not have access to the Internet, so public initialization actions cannot fetch resources. What should you do? The options are: Option A, deploy the Cloud SQL proxy on the Cloud Dataproc master. Option B, use an SSH tunnel to give the Cloud Dataproc cluster access to the Internet. Option C, copy all dependencies to a cloud storage bucket within your VPC security perimeter. Option D, use Resource Manager to add the service account used by the Cloud Dataproc cluster to the network user role.
To arrive at the correct answer, we focus on the keywords: deploy additional dependencies, Cloud Dataproc cluster, startup, initialization action, do not have access to the Internet.
The correct answer is option C, copy all dependencies to a cloud storage bucket within your VPC security perimeter.
Why is this correct? C. Copying dependencies to a cloud storage bucket within your VPC allows the Dataproc initialization actions to securely fetch necessary resources internally, fully complying with the policy that prohibits Internet access. Why are the others incorrect? A. The Cloud SQL proxy is used for secure connections to Cloud SQL databases, not for fetching or deploying file dependencies to cluster nodes. B. Providing Internet access via an SSH tunnel explicitly violates the stated company security policy that nodes must not have access to the Internet. D. Granting the network user role allows the cluster to use shared VPC networks but does not host or deliver the required dependency files.
You need to choose a database for a new project that has the following requirements: fully managed, able to automatically scale up, transactionally consistent, able to scale up to 6 TB, able to be queried using SQL. Which database do you choose? The options are: Option A, Cloud SQL. Option B, Cloud Bigtable. Option C, Cloud Spanner. Option D, Cloud Datastore.
To arrive at the correct answer, we focus on the keywords: fully managed, automatically scale up, transactionally consistent, scale up to 6 terabytes, queried using SQL.
The correct answer is option C, Cloud Spanner.
Why is this correct? C. Cloud Spanner uniquely meets all requirements. It is fully managed, horizontally scalable, provides strong transactional consistency, handles datasets well beyond 6 terabytes, and supports standard SQL queries. Why are the others incorrect? A. Cloud SQL is a managed relational database that supports SQL and transactions, but it does not automatically scale up compute resources to seamlessly accommodate increasing workloads like Spanner does. B. Cloud Bigtable is a NoSQL wide-column database that is not transactionally consistent across multiple rows and cannot be queried using standard SQL. D. Cloud Datastore is a NoSQL document database, meaning it lacks support for standard SQL queries.
You work for a mid-sized enterprise that needs to move its operational system transaction data from an on-premises database to GCP. The database is about 20 terabytes in size. Which database should you choose? The options are: Option A, Cloud SQL. Option B, Cloud Bigtable. Option C, Cloud Spanner. Option D, Cloud Datastore.
To arrive at the correct answer, we focus on the keywords: operational system transaction data, 20 terabytes in size.
The correct answer is option A, Cloud SQL.
Why is this correct? A. Cloud SQL is a fully managed relational database service suitable for operational transaction data. It easily accommodates a 20 terabytes database, as it supports up to 64 terabytes, making it the most practical choice for a mid-sized enterprise without requiring complex global scaling. Why are the others incorrect? B. Cloud Bigtable is a NoSQL wide-column store optimized for low-latency, high-throughput analytical workloads, not for migrating traditional operational transaction data that requires relational database features. C. Cloud Spanner is a globally distributed relational database. While it handles transactions, it is unnecessarily complex and expensive for a 20 terabytes database that comfortably fits within Cloud SQL limits for a mid-sized enterprise. Why are the others incorrect? D. Cloud Data Store is a NoSQL document database. It lacks the strict relational schema and complex querying capabilities required to seamlessly move and manage traditional operational system transaction data.
You need to choose a database to store time series CPU and memory usage for millions of computers. You need to store this data in 1-second interval samples. Analysts will be performing real-time, ad hoc analytics against the database. You want to avoid being charged for every query executed and ensure that the schema design will allow for future growth of the dataset. Which database and data model should you choose? The options are: Option A, create a table in BigQuery and append the new samples for CPU and memory to the table. Option B, create a wide table in BigQuery, create a column for the sample value at each second, and update the row with the interval for each second. Option C, create a narrow table in Bigtable with a row key that combines the computer engine computer identifier with the sample time at each second. Option D, create a wide table in Bigtable with a row key that combines the computer identifier with the sample time at each minute, and combine the values for each second as column data.
To arrive at the correct answer, we focus on the keywords: time series, millions of computers, 1-second interval samples, avoid being charged for every query executed.
The correct answer is option C. Create a narrow table in Bigtable with a row key that combines the computer engine computer identifier with the sample time at each second.
Why is this correct? C. Bigtable is optimal for high-throughput time series data. A narrow table design with a row key combining identifier and timestamp maximizes read/write efficiency, scales indefinitely, and uses provision capacity to avoid per-query charges. Why are the others incorrect? A. BigQuery charges per query based on the amount of data processed, directly violating the requirement to avoid being charged for every query executed. B. Frequent row updates are an anti-pattern in BigQuery. Additionally, this approach still incurs BigQuery's per-query data processing charges, violating the pricing requirement. D. For time series data in Bigtable, a narrow table, tall and narrow, is the recommended best practice. Grouping seconds into columns, wide table, unnecessarily increases schema complexity and makes querying less efficient.
You want to archive data in cloud storage. Because some data is very sensitive, you want to use the Trust No One (TNO) approach to encrypt your data to prevent the cloud provider staff from decrypting your data. What should you do? The options are: Option A, use Cloud KMS keys to create a symmetric key. Then use Cloud KMS Encrypt to encrypt each archival file with the key and unique additional authenticated data, AAD. Use CTLCP to upload each encrypted file to the cloud storage bucket, and keep the AAD outside of Google Cloud. Option B, use Cloud KMS keys to create a symmetric key. Then use Cloud KMS Encrypt to encrypt each archival file with the key. Use CTLCP to upload each encrypted file to the cloud storage bucket. Manually destroy the key previously used for encryption, and rotate the key once. Option C, specify customer-supplied encryption key, CSEK, in the .boto configuration file. Use CTLCP to upload each archival file to the cloud storage bucket. Save the CSEK in Cloud Memory Store as permanent storage of the secret. Option D, specify customer-supplied encryption key, CSEK, in the .boto configuration file. Use CTLCP to upload each archival file to the cloud storage bucket. Save the CSEK in a different project that only the security team can access.
To arrive at the correct answer, we focus on the keywords: archive data in cloud storage, trust no one, prevent the cloud provider staff from decrypting your data.
The correct answer is option D, specify customer-supplied encryption key, CSEK, in the .boto configuration file. Use CTLCP to upload each archival file to the cloud storage bucket. Save the CSEK in a different project that only the security team can access.
Why is this correct? D. Customer-supplied encryption keys, CSEK, ensure Google does not permanently store the encryption key, fulfilling the trust no one approach by requiring you to explicitly provide the key. Why are the others incorrect? A. Cloud KMS keys are managed by Google Cloud, meaning the provider retains access to the keys, which violates the strict trust no one requirement. B. Using Cloud KMS fails the trust no one requirement as Google manages the keys. Additionally, destroying the key makes the archived data permanently inaccessible. C. Cloud Memory Store is an in-memory, volatile data store designed for caching. It is entirely inappropriate and unsafe for permanent, secure storage of critical encryption keys.